Induction cooktops are stoves that utilize electromagnetism and Foucault's currents to be more energy efficient and can heat quicker than its competitors. But how does it work? To explain this, we have made a demonstration that simplifies the concepts of the induction stove.
Before we begin this demonstration, here are some safety precautions that we took while running it. We made sure that we didn't touch any wires that have electricity running through them. We made sure not to touch hot objects. And we made sure not to knock equipment over.
For this demonstration, we used 2 temperature sensors, a multimeter, 2 thick wires, a solenoid, a small iron disc, 2 thin wires, a power supply, some masking tape, and 2 iPads.
First, we wanted to verify that electromagnetic induction was actually occurring and all of our equipment was working correctly. We set up the power supply on alternating current, switching constantly just like in an induction stove, and connected a solenoid to the power supply. We put a second solenoid beside the first one we were powering without connecting the two physically, but when we turned on the first solenoid, there was a small but definite amount of voltage flowing through the second solenoid, measured with the multimeter. Now that we knew that we could induct electricity wirelessly, we went on with our actual proof of induction heating.
Now with the demonstration, we had a similar setup, but we had 1 solenoid and we taped an iron disc with a temperature probe to the center of the solenoid. We put the iron disc inside the solenoid because the magnetic field is greatest there. Then we put another temperature probe besides the disc on the inside of the solenoid.
Our initial trial of the demonstration was not successful, as we did not expect the solenoid to heat up so much. We used plasticine instead of tape to secure the disc, and the heat of the solenoid caused the plasticine to melt before we could get any good results.
We tried it again with tape, which worked better. As we kept increasing the voltage and letting it run for a while, the disc vibrated more and its temperature started rising. We can see that at 220 seconds, the disc's temperature has risen to 40 degrees, but the solenoid's temperature is only at 30 degrees. This proves that it's not just the solenoid's heat transferring to the disc, but there's something else causing it to heat up.
This something is called eddy currents. Eddy currents are currents caused by a magnetic field that is altering in direction. In our demonstration, the eddy currents are created in the iron disc, and the iron disc's resistance causes it to heat up.
In a real induction stove, the iron disc is a pan and the solenoid is bigger and flatter. The current alternates faster, so the pan does not vibrate, and the voltage is stronger, so there's more heat generated. The result of this is a stove that can heat up faster and more evenly, is more energy efficient and environmentally friendly, and is a lot safer than electric or gas stovetops because the surface of the stove doesn't get hot. In Asian countries, induction stoves are very widespread in restaurants because of these properties. Even in the West, induction stoves are popular and getting more common in homes. All of this was achieved using the magic of electromagnetism.